Hello everyone. What I've just shown you here is an example of a classic fluid vortex. So as you can see that when I was spinning the bottle, the fluid inside was forming a tornado-like shape, otherwise known as a vortex. Now I've let the bottle go and you can see the fluid inside has come almost to a complete stop. These are the characteristics of a regular fluid such as water, but today our presentation is going to focus around superfluids and what they are. So what is a superfluid? Well, the main thing to understand is a superfluid is a state of matter in which liquid displays no viscosity and therefore has a negligible loss of kinetic energy and friction. Now, if we apply that rule to this experiment that I've just done, if I spun it again like this, the superfluid inside would continue to spin in that vortex shape, and this is called a quantum vortex.
The most common type of superfluid is superfluid helium-3 and 4. Both these fluids can be classified as helium-2 superfluid. Now, the helium-2 superfluid is created by cooling helium to 4.21 Kelvin and above a temperature of 2.17 Kelvin, called the lambda point for helium. This process creates the colorless liquid called helium-1. When cooled below the lambda point, part of the liquid enters a state called helium-2, which makes it a superfluid.
Superfluids are a window to quantum mechanics and thus exhibit very strange behaviors. Now, this may be unbelievable, but it's very much true. Superfluid helium can actually climb walls. Being a fluid, such a notion may seem absurd. However, there is an explanation. What actually happens is that superfluid helium-4 displays a creeping effect and is capable of escaping any non-closed container as a very thin film, 30 nanometers thin in fact. This film is referred to as a Rawlins film. Due to this thin film, superfluid helium-4 has the ability to escape from capillaries of 100 nanometers or greater. Now, how does this relate to what Rahul mentioned? Well, since superfluid helium has no viscosity, the capillary forces, which are a combination of surface tension and adhesive forces, in the film can actually overcome the gravitational forces, and thus superfluid helium-4 can actually climb walls. In fact, as a result of the no viscosity, superfluid helium can actually also sink through pores of certain containers through which regular fluids cannot. The history behind something is always crucial. It provides an understanding, teaches lessons, and acts as a window to the future. The history of this phenomenon was actually sparked by intrigue with the notion of absolute zero. It was Dutch physicist Kamerlingh Onnes who wished to investigate how materials behave when cooled to near 0 Kelvin. As a result, he liquefied helium for the very first time, and this was one massive leap forward for physics. After years of further experiments, in 1936, Don Misner found that the viscosity of the liquids decreased sharply as the temperature went below the transition threshold of lambda, thus being first evidence of helium-2 exhibiting behavior quite different from a classic fluid. And finally, a year later, Don Misner and co-workers John Allen and Piotr Kapitska studied the thermal conductivity of helium-2 in thin glass capillaries. It was this study that led to the discovery of non-viscous flow in the capillaries, and thus helium-2 was declared as a superfluid.
With superfluid helium-2 defined, we can mathematically calculate motion for the superfluid component in a simplified formula, given by Newton's law. The mass of the superfluid is defined as m4, or rather molar mass of 4 helium. Vs is the velocity of the superfluid component of helium-2, and T is defined by the ratio of increase of the velocity when an object or the fluid moves. With this formula, superfluid hydrodynamics can be applied to real life, as scientists can predetermine the fluid's motion and velocity and take safety precautions based upon them.
Alright, now that we've talked about the theory behind superfluids, I'm going to get into one of superfluids' most recognizable applications, and that is the superfluid gyroscope. So with me, I've brought a mechanical gyroscope. So before I demonstrate this, we need to understand what a gyroscope is. So a gyroscope is a device like this one that uses Earth's gravity to measure its rotational axis on any type of moving body, such as a plane or a rocket ship. So let's see how this gyroscope works. Okay, so a superfluid gyroscope uses both the principles of this and the bottle experiment that I did earlier, and combines it to form a superfluid gyroscope. So the most important thing to understand is that superfluids, as we mentioned before, are very free-flowing and therefore can detect the slightest changes in any rotational axis of a body. This ability to realize very small changes is what makes a superfluid gyroscope 100 million times more accurate than a mechanical gyroscope such as this one. So the superfluid helium in a gyroscope forms a toroid, or a donut shape, with the fluid moving in a perpendicular plane to the actual donut. So these two images here represent the apparatus of a superfluid gyroscope and the actual movement of the fluid inside the gyroscope. So these types of gyroscopes are still not commercially used because they're being improved upon daily, but many high-tech companies have started to make the switch from a mechanical traditional gyroscope to this new type of technology. So the fluid inside these gyroscopes demonstrates something known as the Josephson effect, which basically states that the superfluid will continue to move in the gyroscope for an extended period of time, meaning that they're continually in operation. These gyroscopes also use something known as a squid, as you can see in this image to my right. The squid is a very sensitive magnetometer that is used to measure very subtle changes in the magnetic field. In fact, the magnetometer is so sensitive that it can detect fields 5 times 10 to the negative 8 Teslas weak. Another reason the superfluid gyroscope is so very useful for small changes. Now, this technology, as I mentioned earlier, isn't used everywhere, but because one of the main reasons is because it's so expensive to construct and leave in operation. This is because the superfluid must constantly be kept at a temperature of 3 Kelvin in order to remain at that superfluid state. But improvements are being made daily, and hopefully in the future, many other companies will start to have used this technology.
Another application of superfluids is in satellites. The Infrared Astronomical Satellite, or IRAS for short, was cooled by 720 liters of superfluid liquid helium. This superfluid is pumped to keep the hardware, specifically the infrared sensors, of the satellite at a temperature less than 2 Kelvin. The pumper inside the satellite used the fact that superfluids can seep through small cracks or air holes to pump the helium to the satellite's various sensors. The helium diffused through a brass plug, which contained holes through which liquid or air may pass to achieve a pumping effect. The plug was built inside the vents of the satellite and acted as a superfluid helium vapor separator in the zero gravity. The plug was designed to have the least impact on the temperature of the helium in the satellite, which was cooled at 1.6 Kelvin, requiring only a small pressure drop across it to allow for release of helium. Using this method of cooling, the IRAS was the first ever space telescope to perform a survey of the entire night sky at an infrared wavelength.
Oh, so superfluidity still remains as a large topic of mystery in the world of physics. However, with the information now known, the future of superfluidity is exciting. There has been a curious thought that's been raised. Can light attain a state of superfluidity? Well, in order for a superfluid to be attained, there has to be a critical velocity. A critical velocity, in the case of helium, is when the atoms have minimal energy and cannot move as much. So for light, this has not been proven. However, it has been hypothesized that perhaps a critical velocity can be attained for light in a non-linear medium. So perhaps superfluid light is actually a possibility. In fact, furthermore, when speaking of light and superfluidity, a superfluid helium can actually slow down and stop light for a momentary period of time. So now it has been hypothesized that if we can stop light for even a minute, as it has been proven, then maybe we can encrypt data upon it and then send that data. This can lead to a very exciting and efficient future in quantum computing.
Well, there you have it, folks. Throughout this presentation, we've discussed what superfluids are, superfluid vortexes, superfluid gyroscopes, superfluids in satellites, and even superfluids in light. Now you guys know what superfluids are, why they're so special, and how they're continuing to improve upon them daily, and new discoveries that are being made every single day. We'd like to thank you all for listening to this presentation about superfluids, and we hope you learned something new.